So now we will look at the various different kind of other problems, and we will see how it can be solved in multiple ways. One could be the tedious one, and one could be the easiest one, using our basic principles which we have learned, or of the using the direct distribution problems and subsets or something like that. So let's take an example. So the power set of S is denoted by PS if and PS is nothing but the set of all subset of S inclusive of S and the empty set. Find the number of elements in PS where S is equal to 1, 2, 3, 4, 5. So we can simply try to enumerate all the subsets of S. So first is, let's say, 5. Then all the subsets could be a single entry subsets like this till 5. Then subset of 2-digit numbers, combination of that, so that can be represented like 1, 3, 1, 3, and all the 2 ones. Then we can have subset of all the 3 ones, right, like this, 1, 2, 4, and all those things. Then we can have subset of all the 4 ones. You can simply 3, 5, and like that. And finally we will have a final subset which is 1, 2, 3, 4, 5, right? Now if you have to compute this, then this is nothing but selecting 0 objects from 5 objects. So that is nothing but this part is 5C0, and this is selecting 1 object out of 5 objects, so that will be 5C1. Similarly, this can be represented as 5C2, and this can be represented as 5C3, and this can be represented as all such sets, and this will be 5C5. So our final result will be nothing but 5C0 plus 5C1 plus 5C2 plus 5C3 plus 5C4 plus 5. So you can C5. You can actually find all those numbers and add it, or what you can do is that take a binomial like this. So this is nothing but 1 plus 5C1 x plus 5C2 x square till 5C5 x5, right? So if you put x is equal to 1, you will see that this is what we are looking for, and that is nothing but 2 to the power 5, right? Similarly, if there are n objects in a set, then the total number of power set of an object set will be 2 to the power 9, and in our case it will be 2 to the power 5. But let's try to look at it in a slightly different way, right? So we represent, so let's try to find a bijection. So we say there is a clear-cut bijection between this and 5-digit binary number, where if the ith number comes into the subset, we represent it by 1, or else we represent it by 0. So if that is the case, then this number is nothing but 5. So 1 appears. So we write 1 for the first place and rest 0. Similarly, we write for 2 the first place and rest 0, and henceforth like this we write it 0, 0, 0, 0 and 1. In this case 1 and 2, so we write it as 1, 1, 0, 0. In this case we write it 1, 0, 1, 0, 0, right? So 1 and 3 is there, right? So for these two numbers are represented by 1. In this case we write it as 1, 1, 1, 0, 0, and in this case we write it as 1, 2. The fourth place is 0, right? And similarly in this case we write it as 1, 1, 1, 1, 0, and finally in this case we write it as 1, 1, 1. So we can clearly see that this is a clear-cut bijection, right? So now we are with it's easy to now find the number of 5-digit binary sequence, right? Binary sequence, right? So we have 5 places to fill, and we have 0 and 1 as 2 options. There is no restrictions. You can simply fill it via 2 to the power 5 base, right? You can also think this as a placing 5 objects five different objects, which are 1, 2, 3, 4, 5, into two distinct box. The boxes are your zeros and ones. So the way we have defined zero is that if the subset is not there, if the element is not in the subset, it is defined as zero, and if the element is there in the subset, it is defined as one. So we define two boxes, distinct boxes, 0 and 1, and then we distribute it without any restriction. So that will be five distinct balls in two distinct urns with no restriction. So that will be again k to the power n, which is 2 to the power 5. So you can see that the same problem can be solved by various ways. So, but in any of your competitive exams, you need to be good at finding the easiest solution so that you arrive at the solution quite easily, right? So now let's take a look at some of the more examples which we can have. So this is the next example which we'll be talking about. So let's try to increase the font a little bit more. Yeah. Suppose that the next question says, suppose that five distinct objects A, B, C, D are distributed in three distinct boxes, and that ordering of object in each box matters. How many ways this can be done, right? So you can simply do that. So let's say ordering is not important. So that question is a simple distribution problem of distributing five objects or five balls in three urns. So that will be given by your that will be given by 5 plus 3 minus 1 and 3 minus 1, right? Because there are three urns and five distinct objects, so that is nothing but C2. But there are five distinct objects which are distributed. So these five distinct objects can be rearranged into 5 factorial 5 ways, as we have seen in our arrangements, right? So this will be nothing but 7 into 8, 7 into 6 divided by 2 into 5 into 4 into 3 into 2 into 1, right? So that you will see this is nothing but 3 into 4 into 5 into 6 into 7, right? So you can cancel this one. So this is saying that this will be if there are n objects, and so we have, let's try to generalize this with the same problem, given that we have n distinct objects and k distinct boxes, right? So that the ordering of the object in a box matters will be nothing but you start with k, then you multiply with k plus 1 till you do it n times, right? So that will be k plus n minus 1, right? So this is the output. Now let's look at the third kind of a problem here. So let's try to see another problem now. So we have this problem, okay. Let's see what we have. Okay, so this is our next problem, which says 4 identical objects A, 3 identical objects B, and 2 identical objects C are to be distributed in 9 distinct boxes, so that each box contains exactly one object. How many ways this can be done? Now we know from our table, if there are n distinct objects and same n distinct boxes where each of them exactly contains one object, that is given by factorial n, right? That is given by factorial n. So we have 9 objects and 9 distinct boxes, so that will be given by factorial 9, right? Or simply you can see as, if let's say all the objects are distinct, right? So it just converts into arranging 9 different objects or into 9 places, right? So that will be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. So that will be 9 into 8 into 7 into 6, 5, 4. Using our multiplication principle, that will be again factorial 9, right? But here we see that there are four identical objects A, right? So we have taken into this case all the arrangements with all the objects are distinct. But since four identical objects are A, so we need to divide with all the identical ones. This is the four ones. Then three ones can be arranged into three ways. So we need to divide it by three ways. And the two ones, two identical objects can be arrange into different ways. So this is one way of approaching this problem. There could be another way is like this. So what you do is that first you select out of these 9 boxes, select 4 identical objects, right? 4 identical objects of A. So that can be done via that could be done via NC4 ways, 9C4 ways, right? Now we are left with the 5 objects, right? Because we have selected 4. Now select 3 identical ones from 5. So that will be 5C3. And finally we select 2 out of 2, right? And using our multiplication principle, this is the way we can select them. So this will be again, if you look closely, it will be same as factorial 9 divided by factorial 4 divided by factorial 3 divided by factorial 2. Yeah. The same problem can be approached via different ways, but you see, if all the objects are different, then it is easier to find factorial n, and then there are 4 identical objects. So these 4 identical objects, if they are different, then it can be arranged into factorial 4 ways. You need to divide it 3 different identical objects. If they are distinct, then this will give you the same arrangements. So that then you need to divide by factorial 3 and factorial 2 henceforth, right? Now let's take example. Take the third example, which we have. Okay, so we have taken the 3 cases. Now let's take this one. So what it says is simple. Consider the following 3 arrangements of 5% ABCD in a curved circle. The 2 arrangement of n objects in a circle are considered different if and only if there is at least one object whose neighbor on the right is different in 2 arrangements. Find the number of arrangements in a 5 in a circle. So it clearly says we have to arrange 5 questions ABCD in a circle, and how many ways this can be done. Please note ABCDE is considered same as BCDEA in a circular form, because these are the same arrangement. If you put here B, you put C, you D, E, and then you put A, right? So how many ways this can be done? So now looking into this problem, what we can think of it is that cut, let's say, from point A and make it a straight line, right? So this circle can be cut from point A, and we can simply form a straight line starting with A, and we are left with the 4 places, right? These are the 4 places which we are left with, and we need to arrange these 4 objects B, C, D, E such that it will be same, right? So that will be nothing but this can be done by a 4, 3, 2, 1 way. So that will be factorial 4. So if you have to arrange 5 persons in a circle, that will be 5 minus 1 to the power 4, factorial 4. Similarly, for n objects, arranging n objects in a circle, it will be nothing but n minus 1 factorial, right? So this marks the end of our series of the counting. From the next lectures, we will move into the probability. So we will approach the probabilistic theory, and we will see what are the principles behind the probability and all those things, right? So I have given you all the principles, methods which can be used to find the different problems in counting. If you want to if you want to see more such videos, you can subscribe our channel or visit our website deepdivemaths.com. Thank you.